Thank you for inviting me. So I'm going to present a presentation on self-supervised multimodal geospatial learning, which is some work I've done during my PhD. So just an overview on my work. So I can split it into two big axes, one being the learning of global scale geographical representations, and the one where this presentation is going to focus on learning representation from multimodal Earth observation. So first, I'd like to present what is a foundation model. So basically, a foundation model is just a function that is going to map a structured input, such as an image, to an embedding. Then this embedding will be used in several downstream tasks, which can be like really various. And the idea is to have this embedding to have gathered the most information possible and to be the easily accessible possible. Here we want this kind of black box foundation model to be usable by all real scientists from the world, such as ecologists, such as like mapping agencies that are just going to use a linear regression or a random forest on the embedding that the foundation model is going to produce. So we all know foundation model in vision that works like really well. There is DynoV2, there is SAM, there is CLIP, but what makes them really powerful is that the fact that they are really big, that they see many tokens. I believe it comes mainly from their training set, which is large, diverse, but really important, which is curated. As you see, this is the training data set of DynoV2. It's also a composition of a lot of different things to have the most diverse training set possible. But all of this is really easily because it's natural images. Natural images are homogeneous. You can easily merge different data sets. But when you are thinking about Earth observation, it's much harder to merge data sets because it comes from different input sources, different satellites that have seen different processing. And so it's usually foundation models are just trained on a single data set and are like specialized to a specific sensor. And this enables them to not be that useful. So what we want is to do self-supervised learning across different sensors, resolutions, scales, and data sets to have the most versatile possible foundation model. And that is going to be also able to generalize to new input configurations that he has never seen. So for Earth observation, we have a multimodal alignment. The most famous one is aligning images to text. But here, for Earth observation, we have like optical images, we have radar images, we have hyperspectral images, really high resolution images. We have a ton of different captors that just captures the same information. But they capture different information because these are different sensors. But in the end, they encode the same semantic because they capture exactly the same place on Earth. So we would like a good representation for all those different modalities to be consistent because you capture the same region across all sensors, so you want the representations to be consistent. But you also want to be able to reconstruct missing inputs, meaning that you are able to learn all the different sensor configurations. So when we are talking on reconstruction, this evokes masked autoencoders. This is a famous self-supervised learning method where you're just going to mask part of the image and try and train a model to reconstruct this full image. In doing so, the model is going to learn good representations that are going to be useful for a lot of downstream tasks. So we developed a cross-modal MAE. So given three different modalities, we're going to just encode each one of them, and we are going to align them, meaning that each part of the image should be close to the different corresponding images. Then we are going to merge them into unimodal tokens. But once we have aligned all those different modalities, we can think maybe we just converge to like the common knowledge across those modalities, and we don't want that. We want to still keep the specific information of all the different modalities. And to do so, we're going to ensure we have kept all these modalities by asking the unimodal token to reconstruct all the different modalities. But reconstructing pixels has a lot of drawbacks, especially in Earth observation. There are a lot of disruptors that are not semantic, that we don't really want to reconstruct, or the embedding to have this knowledge. But it has such an influence on pixels that the model will have to retain this information, and it will be the main information he has to learn. And also, for Earth observation, we have like really different sizes of images, depending of if you want to work at coarse level or really fine grain. For example, there are sometimes datasets of 6x6 images, and others that are like 5,000 pixel size images. But rescaling will be always an issue. If you rescale a 6x6 image to 256, which is like kind of the standard size, this is going to lead too much complexity for nothing, and downsizing an image will always lose lose information. So the first solution about reconstructing the pixel is to reconstruct in feature space. So we adapt JEPA, which is a joint embedding predictive architecture. Basically, what we're going to do now is reconstruct the embedding that a teacher is going to produce. This allows the model to discard an information if it finds this not useful. I mean, it could still learn the time of the day or if there is snow or not, but it's not forced anymore to do so. And the second solution is to have scale adaptive encoders. So we're going to define the patch size at inference time. Given an image, we're going to define the size of the patch we want, and then we're going to aggregate the information in this patch to just get our patch encoding. This is done with a transformer, so basically it's a two-stage transformer. Now we are able to process highly different input type. We're going to create a composite Earth observation dataset, which we try to be as much diverse as possible. And we get that's like the boring part, but we get like really good results in air probing and in fine tuning across a different set of benchmarks. But the main issue of this approach is that we still had a projection that was defined by modality. What we want now is to have all the weights of the model that process all the modalities. Here, if we want to have a new modality, we need to fine-tune the model because he has never seen this. So how can you represent an Earth observation in a unified way, knowing that you have spatial resolution that goes from 10 centimeters to more than 100 meters. You have different spectral resolution with like RGB images or more than 500 bands hyperspectral images, or even temporal resolution with satellites that are able to capture each place on Earth every 5 days. The idea is to define an Earth observation image as a scalar value among three axes. There is the spatial one, the temporal one, and the spectral one. With this representation, we can have a unified way to represent every type of Earth observation acquisition we can get. Now, so we define a patch, so as a cube across these three dimensions we defined. It's basically the generalization to temporal and spectral dimension of the previous model IG. And we're going to project this scalar value to a certain dimension that we keep low because of it's quite an expensive step to have just an embedding of each scalar value along the three axes. And we define the Universal Patch Encoder, which will be an encoder that is going to be able to process any type of cube to only one embedding. For this, we're going to just sequentially collapse every dimension with an axial cross-attention. So the final output is just the vector that is going to represent the observation. So as I said, the key advantage of this patch encoder is that we will be able to process any patch of any size from any modality. What is an axial cross-attention? It's basically just an attention along the axis we want to aggregate. And we have linear time complexity and memory in doing so, and it's much more efficient than having a full attention across all your axes because of the quadratism of the attention. Now that we have a universal patch encoder, we're going to define the new architecture. So every image will be processed by the universal patch encoder to produce representation. Then we're going to still do an axial cross-attention, but on the modality axis to produce unimodal representation. And then we'll have the regular self-attention of a vision transformer. But as real-world scientists want some really fine grids, like often pixel size embedding a map, we're going to also have just a usable output resolution, definable output resolution, and we're going to skip all the most fine-grained spatial information to a cross-attention to feed this new target grid. Now that we have a model, we have to train it. So the first step is to drop a lot of information. We have more than 80% of pixels that are being dropped. We drop full modalities, we drop some patches, we drop channels and timestamps, and we are going to try to reconstruct them. So we have two losses. We have the same losses as before, which is the consistency loss. It's just a contrastive loss on the output of the universal patch encoder that is going to force consistency across modalities because, again, they capture the same information on the ground, so they should have the same representation. And then we're going to reconstruct the missing input through a random frozen linear projection. It's basically just a trick to not reconstruct pixels but embeddings. And as you're going to reconstruct embedding, you are able to do contrastive and have like much diverse, and this will lead to much diverse representation and avoid a lot of collapse mode. Again, we try to have a composite dataset. Here it's even bigger than the previous one with new modalities we were not able to handle before, with hyperspectral, with DSM. With the most sensor we were able to get in order that if we take a new sensor, it will kind of fall in the convex hull of all what the model has already seen. That was the goal here. Now, in terms of results, as UniverSat is able to process any type of information, it is also able to be evaluated on all benchmarks and being evaluated against models that are really specialized on different modalities, also through linear probing. So we are able to be competitive with really specialized model on the most common data sets, and on other kind of harder data set where models have to learn an upper net, we are able to be really competitive with only a linear. And even more, we are able to compete on hyperspectral benchmarks where all the other models are not able. This benchmark is done on Nmap data, which is a modality that the model has never seen during the pre-training, and we are still able to get really competitive results to beat models that have been trained on this modality, and even to be competitive with really specialized model on those benchmarks. A bit of qualitative results. We are able to produce feature map at the size we want. So to produce feature map which are really fine-grained, and this allows us to be even competitive with embedding fields, which are just embeddings that are released throughout the globe and have seen a lot of different data. All the code of what I've presented is open source. AnySat and UniverSat are just hosted on the Torch Hub, so they are just accessible from a single Life-on code. And I'd like to thank you for your attention, and if you have a question, I'll be glad to answer it.